this one, we have 4 different terms. And cubic polynomials are notoriously much more difficult to factor, especially when you compare it to the quadratics. But one method that we can use is factoring by grouping. So we can group together maybe the first 2 terms and the last 2 terms. But if you want, you can try and group this a little bit differently. Maybe you can group the 7x squared and the minus 35 because they're both divisible by 7. So you'll want to use your best judgment. But let's just write this out as x cubed plus 7x squared, and then we have the minus 5x minus 35. So like I mentioned, we're going to group the first 2 together and the second 2 together, and then just ask ourselves, what is the common factor here? So x cubed and 7x squared, they don't share any numbers in common, but they do share x's in common. And this has 2 and this has 3, so the lowest amount that we can pull out is 2 of them. So we have x squared, and then what we're left with, we pulled out 2 of the x's, so we have 1 left, and we pulled out the 2 x's here, and so we only have the 7 left. And then of course here, notice that they're each negative, and they're each divisible by 5, so let's pull out a minus 5. And here we're left with an x, and then minus 5 goes into negative 35, positive 7 times. Now, the whole goal of the grouping method is that when we do pair them up and factor out, we should get the same expression in each set of parentheses. And let's say this one, you just pull it out of 5, and you'd be left with minus x minus 7, and you'd notice they're not the same. Well, you would also notice that one is the opposite of the other, and so you would just have to recognize that you need to pull out the negative as well. So sometimes you might not get it right the first time, but you can usually just double check and see if you can pull anything else out. So this method, and let me write it down if you haven't seen the word, this is factor by grouping. And once we've paired them up and pulled out the greatest common factor from each, then we have this expression that's the same in each of these, multiplied by whatever common factor we pulled out. And so we have these 2 terms. This is a term and this is a term, and they share this x plus 7 in common. So just like when we're pulling out the greatest common factor, we can pull out this x plus 7 from each of these. Or essentially, we're dividing each term by x plus 7 when we factor it out. So we pull out that x plus 7, and we're left with x squared here, because like I said, we're just dividing each of these by x plus 7, so it'd cancel out here. And here, we're dividing by this x plus 7, and so you'd be left with this minus 5. It's essentially the same idea if you had x squared times a minus 5a, and noticing that a is a common factor, which you can pull out, and you'd be left with x squared here and minus 5 here. It's just a in this case is this entire expression, the expression x plus 7, so it's a little bit more complicated, but we've been able to simplify this. Now, you could think that this is a difference of squares, and in some sense it is. And there are ways to factor this further, though for the Khan Academy, this is as factored as you'll make it. But if you do want to see how it goes further, let me rewrite this as x squared minus 5. Remember our formula for a difference of squares, that a squared minus b squared is a minus b times a plus b. It's just in our case, we have a as x, but our b would have to be the square root of 5 squared. Since if you take the square root of 5 and you multiply it by itself, you do get 5. And so you could do this where now this is going to factor into a minus b times a plus b. So it factors into the first one, the x, minus the second one, root 5, ignoring the square. And then it's the first one plus the second one. So if you want, technically, you could factor this a little bit further, but this is not always beneficial since now we have these irrational numbers, the square root of 5, in our final product. So it just depends the scenario. Like if this is some polynomial where we're trying to figure out where it equals 0, then this is useful because now we can use that zero product property, and it goes through that x-intercept at root 5 minus root 5 and negative 7. So it just depends the context. but I did just want to mention that this can, in fact, be factored a little bit further, though usually for this exercise, this would actually have to be some perfect square from a whole number. So 25 from the previous example is a good example of that. So let's do another one. And this will be our last one. But now we have some fourth power polynomial, which again, these are very difficult to factor usually. You essentially need a very special version to be able to factor it. In fact, if you change any of these coefficients by just a little bit, maybe even one number, then in most cases it won't be factorable. So these you really have to set up to work, and they don't always work, but you can at least get a general idea of this method because sometimes it does work and it can be very useful. So the one technique we have for these cubic and quartic polynomials is factor by grouping. So we're going to group, let's say, the first two together and the last two. Though if you want to experiment by grouping different ones, you can try that as well. Maybe the x to the fourth and the 4x and the 5x cubed and the 20. And it will work just the same. It'll look a little bit different during the process, but the end result will be the same. So from these first ones here, we can factor out 3 of the x's. Since there aren't any numbers we can factor out, since the coefficient on this is 1, but they each have x's, and this is the lowest amount. So we can pull out an x cubed, and we pulled out 3 of the x's, so we have 1 left, and we pulled out all of the x's here, and so we just have the 5. Now from our next one, this 4x plus 20, 4 and 20 are both divisible by 4. So let's factor out a 4. They don't have x's you can factor out since 20 doesn't have an x. So we can just factor out the number 4, and dividing each of these by 4, this would just be an x, and this would be a 5. Now, of course, if you want, along the way, you can redistribute, prove to yourself that if you did that, you would get back what you started with. And notice that from each of these terms, this term and this term, they each share this x plus 5 as a common factor. So we can factor that out from each of them. So if we pull out x plus 5, remember we're essentially just dividing now each of these by x plus 5. And here they would cancel out and you'd be left with x cubed. And here they would cancel out and you'd be left with 4. So this will be our final answer because there's no easy way to factor this. It's not a difference of squares. It's not a quadratic. So we'll just leave it as this cubic. Now, sometimes you can factor cubics, but we're looking for the case where you have a cubed plus b cubed, which actually has a fairly complicated formula, which looks like a plus b times a squared minus ab plus b squared, though in our case, 4 is not a perfect cubed. So our b term in this case would be the cubed root of 4, which is fairly messy. So we're not going to factor that any further, though technically you could if, for instance, you were trying to figure out when this is equal to 0. That might be beneficial to use it. And just so you've seen it, and let me write out what this is called. This is a sum of 2 cubes. And there's actually, for cubes, there's a difference as well. So we could have a cubed minus b cubed, which is going to factor very similarly into a minus b times a squared plus ab plus b squared. And notice the formulas are very similar. This is this is a difference now because we're dealing with subtraction of 2 cubes. And the way to tell them apart is that notice this first term with just the a plus b, it has the same side, and then the sign switches for the next one. And this sign at the end is always going to be positive. But notice it's the same here. You have the same sign in the first one, then it switches to the opposite, and the last sign is always going to be positive. So that's one way to remember the difference between the formulas, is that they have the same first sign, the opposite second sign, and then the last one is always positive. So sometimes you see these, though you're not going to see them usually in these exercises. So I just wanted to mention them because they do exist. It is one of the few factoring techniques we have for cubics. And you might be wondering, is there a sum of two squares? So sum of two squares. Technically, yes, but it's complicated because if you have two squares added together, then these are going to factor into a product of imaginary numbers. You'd have a minus b times I times a plus b times I. And you can see that this is true because if you multiply it out, so distributing the a to each of those, you'd get a squared plus abi. Then if you do the minus bi, you get minus abi. And lastly, minus bi times bi, or bi squared. And when you simplify this, a squared plus abi minus abi. So those middle terms will still cancel out. But now you get minus b squared times I squared. And remember, since I, that's our imaginary unit, that's the square root of minus 1. When you square this, you are squaring a square root. And you get back whatever's on the inside. Because square roots and squares, they're inverse operations. They cancel each other. It's essentially like multiplying by 2 and then dividing by 2. You just get back what you started with. And you can see this is true for other numbers. If you have the square root of 4 and you square that, well, square root of 4 is 2. 2 squared is 4. You get back what you started with. And so this I squared being negative 1, we'll flip this back to a positive. So technically, yes, you can factor these, but we don't often do it because it just leads to more complication with imaginary numbers. And this is not going to help you when you're trying to find, let's say, the zeros or the roots of the polynomial. It won't help you find the x-intercepts because those x-intercepts will be imaginary, which you won't graph it as going through the x-intercept. So I just wanted to mention these other more advanced techniques since sometimes you will encounter them, though in this particular exercise, you won't have to deal with those.